各位同学，我们那个今天下午seminar哦，那我今天很高兴请到Lee-Quantitative的那个大的顾问力来我这边演讲哦。那我这边呢，先简单的介绍一下他哦，他是，对不起。他是这个在1993年呢，在韩国的这个很有可能，Kyungpoon National University 拿到这个学士的学位，后来呢去当兵，在韩国服兵要3年，现在还是3年啊，不像我现在已经。那在98年在这个学校拿到这个硕士学位啊，那后来他就到美国的到加拿大的那个McGill大学去念博士，他在2003年拿到博士学位，后来他留在McGill大学担任 postdoc， 还有这个 researcher， 从2003年到2006年，那从2006年开始到现在，他在 ACA 和 SP 担任这个 postdoc 啊。那我最早注意到他的例是因为我们每隔2年会去参加一次这个国际的ACA7段研讨会，这时候我就发现，说McGill大学有一位韩国的学生，他每次报的这个talk都非常的精彩。后来我们实验室有一位同学叫钟浩生，他毕了业，他也到McGill去念书，那所以他们就更熟了。那我2年前有到McGill去访问，那我也碰到他，所以就跟他慢慢熟起来。那大哥力这次到台湾来是为了要参加5、6月份在南部的那个 T-Rex， 那他带来很多的那个 vertical pointing 跟地面的那个 disrupting 的仪器，哦。那他今天来这边演讲，明天回韩国，5月会再回来，会在我们参加台湾南部的这个实验，所以我们今天很高兴能够请他来。那他讲的题目是非常重要的题目，就是定量降水估计跟定量降水预报 QB 和 QBF。So let's welcome Dr. Lee.
Thank you. This is my great pleasure to be here, and thank you for all the faculty inviting me here. Actually, I had about 45 minutes rest. So that 45 minutes was one of the most relaxing times since I'm here. Okay, so I will talk about on the general overview on the precipitation estimate and the forecast. So it's more the radar-oriented presentation, but I will try to cover all different parts. So you may realize this is a typical rain gauge developed by South Korea a long time ago, about more than 600 years ago. So during that period, between 15th to 19th century, there was a frequent flood, about 2 floods every 5 years. I say it's frequent, but by coming to Taiwan, southern Taiwan for the TMAX, this is nothing actually. So, and also during that period, the measuring vapor amount you have at each location or each province was extremely important to control the water for the agriculture. So this is a necessity that all this development, all this rain gauge development we call Cheobugi. So Cheobugi is basically composed of 3 components here, here, and here. They measure in the unit about 0.25. So they only made record of event based, so they just recorded event total accumulation. So, and also they made several of these Cheobugi and then deployed at the different province. And so we can call that was all this rain gauge network. Unfortunately, right now we have only 200 years of the record from the late 18th century. So here it shows the yearly precipitation amount. So you see a lot of year-to-year variation. But one interesting thing is around this period, late 19th century. This is a period where there is a lot of political corruption in South Korea, and also eventually the Joseon dynasty in South Korea fell down and under the control of Japan. So still it's not sure the change in the weather made a big, the impact in the political situation, or there was some issue of measuring the rain. But a lot of research already showed that this is not an artifact of observation, but that was sort of reality. After 600 years later, we have this kind of modernized rain gauge network. Now we have a better mechanics and better electronics. So still we have about intergauge distance about between 20 to 60 kilometers. So one of the issues is whether we can resolve the precipitation with these types of rain gauge network. So this is the actual rain gauge measurement at around the Alps area. So with a 72 rain gauge. So here you see the some color dark. So the reddish color is over 40 millimeters per hour. So white one is no rain. So by looking at this rain gauge measurement, there is no clue what types of actual precipitation pattern you have. So this was the actual precipitation pattern we had during this same period. So by moving from here to here, there is no clue, or really it's extremely hard to make a connection between your measurement with the true field. So this is due to the limitation in the gauge networks. So we try to put as possible as many rain gauges, but still they are limited in terms of spatial resolution. So we try to find some solution from the remote sensing measurement. So in particular for the radar, ground-based and satellite-based rain measurement. So ground-based radar provides very high spatial and temporal resolution information. But one of the issues with the radar measurement is their measurements are limited over the continent. On the other hand, the satellite provides a little bit lower resolution information. But one of the big issues in the satellite measurement, like GPM or twin measurement, is their frequency in measurement in time. So with the GPM measurement, you may have just a 3-hour time resolution. So still, with those satellite measurement, you cannot completely resolve the small-scale precipitation structure. But one of the advantages of satellite measurement is it provides information over the ocean. So let's say you have a radar measurement. The first step is maybe you can combine the radar measurement with external data like satellite and measurement gauge measurement, and then you can estimate precipitation amount. Those estimated precipitation can be used to analyze atmospheric status like rainwater content. And then those information can be used for the numerical prediction or hydrological prediction model. And also we can distribute those information into the user. And also this precipitation estimate can be used for the verifying numerical model in terms of precipitation amount. But one of the issues when you're addressing the use is precipitation estimate map, the one of the issue is how accurate they are. What's the uncertainty in your measurement? And furthermore, what's the spatial and temporal structure of those there? So those information are extremely important to integrate into the numerical model, in the atmospheric numerical model as well as the hydrological model. So first step in the radar precipitation estimate is understanding or quantifying uncertainty in your measurement, and also quantifying the spatial and temporal structure of those areas. So let's say this is typical radar measurement. We call the radar reflectivity, effective radar reflectivity. The first question is whether our measurements are all from the rain or precipitation. So definitely the answer is no. Some of the information actually coming from return from the nearby ground or building or trees, all those information. And also, we can detect biological target like birds and insects. And also, we have some artifact around here. So, we call there is weak radar reflectivity around this area. This is due to the beam blocking or beam shadow. So, these all artifacts should be corrected to estimate rainfall amount or rainfall intensity. And then, finally, we are interested in the precipitation. Radar measurement only from the precipitation. So one of the key issues is how we can eliminate or correct these the ground return, or we call the anomalous propagation or ground clearing. So first step should be eliminating, identifying these non-precipitation echo, and then eliminate or correct those areas. So we developed a fuzzy logic approach. So let's say from the radar, we measure all different characteristics like the radar reflectivity and radar velocity and spectral width. And from those information, we can calculate the feature like vertical gradient of reflectivity and radar velocity, which are measurable, and standard deviation of radar reflectivity. From this information, we can calculate the membership value for each given feature. And then we can calculate total membership value by combining with the weight for the membership given feature. The one important thing is in this algorithm is how we can identify membership function and weight in an objective way. So a lot of people actually develop this kind of approach, but there is no real way of identifying or determining the actual membership function in an objective way. So we developed a sort of membership function and weight based on the data itself, and then the results show that this provides a lot of improvement in our identification. It can provide as much as like parametric radar can provide. And then by comparing total membership function with certain threshold, we can identify whether it's a non-precipitation echo or precipitation echo. I will show you an example. So this is a 5-hour accumulation from the radar reflectivity measurement. So here, the reddish color or bright color is generally the heavy rain. So here, you see a lot of heavy rain area around this area, here, and here. So this area, actual value is over 200 or 300 millimeter for during the 5 hours. So you will immediately predict that there is the flood around this area. But actually, these heavy precipitation come from the precipitation return or the artificial echo return from the nearby ground mountain. So these are what we call the ground further or the anomalous propagation. So by applying the fuzzy logic approach, we could eliminate all these non-precipitation and artificial heavy rain area, and then we could have original precipitation feature. And we compared with the precipitation estimate from the parametric approach. They provide almost identical result. So here it proves that this type of fuzzy logic approach actually works. So in this way, we can eliminate non-precipitation echo. Now we are talking about actual the radar return from the precipitation. So far we are dealing with just the radar quality issue. The next step is there are a long way to go actually. So there is several sources of error in radar rain estimation. Radar does not provide the rainfall directly. It's an indirect measurement. We have a radar reflectivity measurement. From the radar reflectivity measurement, we want to estimate rainfall intensity or rainfall accumulation. In those processes involve a lot of uncertainty. So I will talk about what types of uncertainty we have to deal with. First one is the instability of a radar, whether a radar is well calibrated. There is overestimation, there is high power or low power, but also depending on the weather condition, like whether high temperature or low temperature, maybe the hardware performance of the hardware vary too. And so we need to calibrate radar at first. And next step is if you are dealing with the short wavelengths, like the C-band radar, 5 centimeter, or X-band wavelength, X-band radar, 3 centimeter radar, then you have a lot of attenuation. So what happens is when the precipitation comes over the radar, the radar becomes wet, and you are losing signal due to the rate attenuation. We call the radon attenuation. Another thing is when we send out microwave, and then when pass through the heavy precipitation area, it's losing additional power due to the precipitation attenuation. So another issue is the radar beam become far and far propagate, and then the beam become broader, and then also measuring height increases. But we are interested in the precipitation measurement at the ground. Also, let's say we want to have a high resolution measurement, but our actual measurement is sort of smooth the value at a very big area, a few kilometer area. So somehow we need to correct this measurement, beam broadening effect. And also, since we are interested in the rain at the surface, we need to extrapolate our measurement into the ground. And then we extrapolate our radar measurement, reflectivity measurement to the ground, and next step is we try to estimate the rain at the ground by transforming or estimating the rainfall intensity with a known ZR relationship or parametric relationship. So this involves the variability of the dropside distribution. So this is the place where the microphysics play key roles. And another thing is, so far we are dealing with the conventional radar, but if you are talking about the dual polarization radar, then you have to deal with whether the shape of a drop, raindrop, or snowflake, whether raindrops are less deformed or more deformed. Depending on this information, you will have a completely different parametric radar measurement. So you have to concern on this part. There are a lot of research whether there is a variation in the drop shape. A lot of people say there is a variation from stone to stone. Someone says we don't care, just apply just mean the shape. But the variation of the shape will provide uncertainty in your measurement. And next step is parametric parameter. We are dealing with the sort of the differential quantity. So this is KDP is differential the phase difference between horizontally and vertically polarized beam. So we are talking about the different quantity, different difference between the two beams. So, and also JDR is the ratio of the power in the horizontally and polarized beam. So due to that fact, we have to deal with the measurement noise in these parameters as well. So in particular, uncertainty in radar measurement, reflectivity measurement is much less. But if you are dealing with the parametric parameter, noise becomes more important. So we have to find some way minimizing the uncertainty or noise in these quantity measurements. So these are all the issues we have to deal with to get the real accurate precipitation estimate from the radar. So let's talk about the first variability of dropside distribution. How the variability of dropside distribution are related with the GR relationship. So this is the dropside distribution. Number density is a function of diameter. Each line is every 1 minute measurement. So from the DSD, we can define nth moment of dropside distribution. From here, how these you see a lot of variation from minute to minute. And how these variations are related with the GR relationship. So this is GR relationship from this data. So you have R, rainfall intensity, and radar reflectivity. So in the radar hydrology, what we are doing is we measure radar reflectivity and get the rainfall intensity using known GR relationships. So here, the rainfall intensity can be approximated by 3.67 moment of dropside distribution. And the radar reflectivity is the 6th moment of dropside distribution. So you are dealing with the low moment and high moment. So low moment has more weight in the smaller drop, and high moment has more weight in the bigger drop. So all these variation will appear as a scale plot, like a large uncertainty around this deterministic line. So this variation of this actual data point from this dark line will appear as uncertainty in your radar measurement, radar precipitation estimate. So this is sort of connection how the variability of dropside distribution are related with the uncertainty in GR relationship. So we need to understand the DST first to reduce the uncertainty in radar rain estimation due to the variability of dropside distribution. That's the first step. But when we talk about variability of dropside distribution, there are several components to control the variation of dropside distribution. First one is whether you have a smaller mean diameter or a bigger diameter. So that's one key component. The other component is whether you have the narrow distribution or broad distribution. And another issue is whether you have a high number concentration or low number concentration. And another issue is what kind of shape of DSD, dropside distribution, you have. these are all the controlling parameter for the drop size distribution. So we need to understand these all variation to improve the radar weight estimation due to the variability of drop size distribution. So the evolution of the drop size distribution can be explained by the stochastic gap growth equation. So this is the equation I will only show. So here, the variation of number concentration can be determined by various components. The first component is the sedimentation effect, and second term is the auto-convergence, and third, this one is the cloud correction, and this is the coalescence and breakup. So for the, it's mostly for the, it's for the rain, it's a raindrop, a liquid phase processes. And also there is deposition for the, mostly for the snow, cold microphysics, and aggregation between the snowflakes and fragmentation for the snowflakes. So these are all the controlling parameters in the changing microphysics, or shape or the mean diameter, or whether it's broad or narrow. So we need to understand all these. But we can simplify this equation based on some specific cases. So let's say if we have extremely heavy rain, then the most controlling parameter, controlling process will be coalescence and breakup. So you can think in that way. So let's say there is a sort of two dominant effect, like sedimentation and cloud collection, like a heavy drizzle case. So in that case, you have there is no cold microphysics, only the sedimentation effect, and cloud collection is a dominant effect. So in that case, you see this, you can derive the solution from this equation, then that will provide this kind of evolution of drop size distribution. As the intensity increases, you see the parallel displacement of drop size distribution.
Excuse me,
Yeah.
this is the CLC. I cannot hear it clearly.
Which one?
The second time, CLC.
The cloud collection. It could be whether ice crystal collecting supercooled water, like the rising processes, that's one process. And the other process is when the rainfall, there is a lot of liquid water at the lower level, then it may collect a lot of liquid water at the lower level. So it's more like a low level growth.
So this including the ice.
This you can interpret. In the middle case, you don't include any the rising processes. But like in the middle case, it's just sedimentation and cloud collection. But in the bottom of the cold microphysics, this will include the rhyming process. Yes.
But the coding classes, you are separate out as the
Right.
red orange.
Yeah. But next one is we can deal with like extremely heavy rain case. Coalescence and breakup will be the dominant effect. So in that case, so typical equilibrium drop, you expect a typical equilibrium drop size distribution. So this part, this microphysical process was particular, the kind of a lot of intention in all the community. So if you go through the literature, you see a lot of talk on this, whether here you can reach the equilibrium drop size distribution, what kind of shape you are seeing due to the equilibrium drop size distribution, and whether you see some peak in your distribution due to the breakup process. So this is one of the mostly studied processes. But again, in this, when you have two dominant coalescence in breakup process, you see that this kind of parallel displacement of drop size distribution, the intensity increases. So the number density increases. The next process is typical Marshall-Palmer type processes, mostly cold rain microphysics. So there is a definition, but maybe weak and moderate aggregation processes are dominant. In that case, you see this kind of pivoting. So the intercept parameter, the pivoting point will be 0, diameter equals 0. So you see the typical Marshall-Palmer type, exponential drop size distribution, and the slope changing due to the intensity changing. But you can think about in this process, aggregation become more stronger, become more dominant. Then this pivoting point move to the large diameter. So you see the pivoting with respect to the medium west diameter. So this is sort of a general, some example of how the microphysical processes actually control the evolution of drop size distribution as a function of rainfall intensity changes. So we need to understand all these processes, and so first step is understanding microphysics and trying to compare microphysics with actual observation. So here, this is actual measured rate, height, time, cross-section of radar reflectivity and total velocity by vertically pointing excellent radar. And this is just measuring the precipitation, what went through, passed through just one column. So here, in general, you see the high reflectivity area, which indicate the melting process, snow above and rain below, and also the velocity, total velocity increases below this melting area. This is sort of typical case you see throughout the year in the Ontario environment. Also, you see the drizzle process around here, which doesn't show any the bright band around the snow reflectivity. So this is purely the warm-lane process around here. But if you look at the more detail, you see that a lot of details, a lot of processes are going on actually. So here, you see the very thick bright band, strong and heavy very thick bright band. Here, and also here you see a lot of convective activity. So it doesn't show any the real strong bright band. So this is typical stratum period, and this is the typical convective period. And also in terms of intensity of bright band, here you have strong and thick bright band, and here we have a very light, thinner bright band around here. In terms of total velocity, you see the height, there is a lot of object around here, indicated by yellow color. Here, this is all object around here. So let's say the object was, here the yellow is around 2 meters per second above the motion. So typically the falling velocity of the snow crystal or snowflakes is around 1 meter per second. So that means here we have typically 3 meters per second of object from this area. And also Doppler velocity here, the blue color is Doppler velocity larger than 2 meters per second. So the snowflakes falling so fast. So that indicates the heavy, high density snow crystal, snowflakes. And here the overall velocity is much smaller than 2 meters per second. It's just falling about 1 meter per second. This is typical aggregate around here. So by looking at this is just one day of a precipitation event, we see all different microphysics processes are going on. In this, at the same location, we have the precipitation occurrence sensing system. This is another small X-band by static radar. This measures power spectra and then convert power spectra into the drop size distribution by taking into account the actual beam pattern. So from here, we have the drop size distribution and calculated the reflectivity and rainfall intensity. So each point indicates the 1 minute DSD measurement. You see a lot of scatter with respect to the deterministic relationships. So a lot of scatter here. That will be eventually uncertainty in your radar rate estimation due to the variability of drop size distribution. But first question, we're talking about whether our uncertainty in the radar rate estimation has a structure. What's the amount of uncertainty and whether they have the structure in time and space. So I will look at both information now. So there is a lot of stochastic component, but question is whether these uncertainty are completely random or is there any structure in time. So here, to see the structure in time, I put the time information now. Previously it was black and then it didn't show any time information. But now we start to see the time information with a different color. So for the initial time period, around the all data point is below this deterministic line. And then move up here and then coming down here and then go here again. You see there's some sort of systematic change along this deterministic line. So that indicates the structure in the uncertainty, in your rate estimation error. So you can you quantify that amount quantity of these uncertainty in terms of structure function, second order structure function, and also decorrelation distance. So with a certain time lag. So here, so structure function as a function of time lag, and also decorrelation function with a lag line as a function of time lag. So here, structure function increases. There is no flattened area or structure function. And also decorrelation is gradually deeply, but even for the 1 hour time lag, you see the decorrelation of correlation of 0.4. So it means in this case, let's say decorrelation distance is you can define decorrelation time as 1 over E, and in this case, decorrelation time is longer than 1 hour. So it means you have the error here, those error structure. So this uncertainty will be completely decorrelated after 1 hour. So you see the systematic change in this uncertainty hour by hour. So those uncertainty basically coming from all the variability of dark side distribution. That is the change of microphysical processes. But this is sort of a striking result. You see the sort of decorrelation distance of 1 hour. So this is a summary for the 5-year geometric data set. And structure function is a function of time lag, and correlation function is a function of time lag for the different types of precipitation. But when we use all the data, then this will be black line. And only for the stratiform rain, we see this kind of blue line, and convective line is here, and or embedded convection with the following stratiform case. So both those two cases, convection, embedded convection with the following stratiform case, you see the decorrelation distance is less than 10 minutes. So you don't see the much correlation in the convective and stratiform rain case. But in stratiform rain, you see the decorrelation distance about time of about 1 hour. So in the stratiform case, we typically think the microphysics is much simpler in the stratiform case. But this stratiform case involves the total microphysics. So due to the whole change in the total microphysics, you see the systematic change in microphysics hour by hour.
What covers the second peak?
This one, I would say this is more like statistical uncertainty because we didn't have enough time data set. We are talking about Montreal area. So the convection is very rare, maybe less than 20, between 10 to 20 cases with pure convection. So around here, the uncertainty is very large. So this is another case we see the sort of distinctive change in microphysics. So here we don't have any bright band around here indicating collision, one lane process. And here you see the typical bright band, and there is a low bright band here. There is an abrupt jump of bright band between this period and this period. So without knowing any microphysical information, you immediately know, you see the so you can identify three periods. Here also this case is happened when we have the passage of one front. You see the wind, how the wind change as a function of time, and also with the height. So here you see the southwesterly around here, and then more like easterly tide or southerly tide wind. So this is the passage of one front. So we see that this kind of change, jump of gradient quite often when we have a passage of one frontal lane band. So in this case, in terms of microphysics, again, this is a one-lane microprocess, and typical stratiform type processes like deposition and aggregation is more like dominant processes. But the aggregation is not that strong enough so far. And if we assume, since in this case there is raining, so by assuming the moisture additive process, we can identify maybe around 3.5 kilometer. We will have a layer of the temperature will be around the minus 6.5 degrees. So in terms of microphysics or irrigation process, around this layer between the minus 6.5 to the around 0 degree, there is the snowflake becomes sticky. So it start to partially melt from the surface. So the snow becomes very sticky. If there is a chance two snowflakes collide each other, then they will make a big snowflakes. So we call that as aggregation process. So this is sort of between this layer, between here and here, this layer is sort of a favorable layer for the aggregation process. But here, if you look at here, this kind of jump of gradient typically occur when you have an isosomal layer in between this layer. So sort of you see the double gradient around here. So temperature between here and here is almost the same. This is almost isosomorphic. So in first period, you have a much thicker layer favorable for the aggregation process. So you have a much more stronger aggregation process for the first period, and this is a typical Marshall chromatite with moderate and light aggregation process. So now we can identify this is a strong aggregation process and typical Marshall chromatite flat forming and warming process. So this case, we see the distinctive GR relationship. For the first period, we see the strong aggregation here, and second period, typical Marshall chromatite. In the last period, we have a digital period. For example, for the digital period, for given reactivity, like here, you have much higher rainfall intensity compared with these two periods. But that's the opposite for the aggregation process, which makes sense. If you have a large aggregate, the reactivity increases rapidly, but the rain mass over your water will be exact same, or just double. So that's why you see you have a much higher reactivity compared with the different processes during the strong aggregation process. So this is indicate that all the variation of variation of drop size distribution as well as variation of GR relationship is controlled by microphysics. Those change of microphysics or those change of GR relation, the differentiation distance is above 1 hour in neutral environment. So you want to nearly update the GR relationship, you need to update GR relationship every hour. So this is a sort of a summary for how the DSD variability, what kind of amount of uncertainty we expect due to the variation of the drop size distribution of microphysics. So we expect sort of a 28% of bias due to the day-to-day variability of drop size distribution. If we use climatological relationship, this is like if you are deriving daily accumulation with the climatological relationship, even for the daily accumulation, you will have a 28% bias. But even within the day, so daily bias in daily accumulation was 28%, but still you have a lot of variation within the day. That will provide around 30% uncertainty, random error in your rate estimation. But when we talk about the variation of microphysics, that will provide around 43% of uncertainty in your rate estimation when you use the climatological relationship. But when you identify proper GR relations for given microphysics, then you can reduce error to 7%. So this is our ultimate goal in the radar rain estimate. So to do that, you need to identify proper microphysics for given time period, and you derive GR relationship, apply that GR relationship for given case. So this is summary for the uncertainty in DS due to the uncertainty in the rain estimation due to the DSD variability. Those uncertainty due to the variation of drop size distribution can be reduced if you have additional parameter. Like in parametric parameter, now you have information on the drop shape. So that information can improve actually or reduce uncertainty due to the variation of drop size distribution. So that's what you see here. So here we compare uncertainty in radar rain estimation with the GR conventional relationship with the parametric relationship when you use the GDR and reactivity. So here for the no average, the instantaneous rain measurement, we have a much higher uncertainty in the parametric approach. This is purely uncertainty in GDR, differential reactivity, because I'm assuming sort of a fast scanning radar. This is a result from the operational environment. So in the middle radar, they are rotating with the 6 RPM, 6 rotation per minute. So with that, we expect this kind of uncertainty, 1 dB uncertainty in the reactivity, and uncertainty in GDR is 0.27. So that's all the random error in your radar parameter measurement itself, in the GDR and the reactivity. So those uncertainty in the measurement can be reduced by doing some sort of simple temporal average. So that can be reduced, GDR uncertainty can be reduced to 0.14 with a 60-minute average. So if you do the 60-minute average, let's say you want to get the hourly accumulation, then you will get now you see the improvement with the parametric approach. So the most of the literature, they show the improvement in the parametric rain estimation. But you should be careful. Most of those experiments based on a very slow scan. So that they scan very slow, just one location per minute. That provides a lot of sampling, a large number of sampling at the given position. So that reduces uncertainty in your measurement. But in the operational environment, there are a lot of different demands. Like in the dynamic side, then they want to get the dynamic information, wind field, with a rapid update. As well as in the severe weather, like aviation, they want to see how quickly, like the severe weather, like microburst or tornado or those thunderstorms develop. So they need to have a very rapid update. At least they want to have a full volume scan every 5 minutes. So to get those information, you need to have a very fast scan that will degrade your quality of your measurement. That will give you the uncertainty, a larger uncertainty in your radar estimation. So far I was talking about the rain only. In this Taiwan environment, you don't need to worry about this one. But this is extremely important if you go to the northern part. In snow estimation, now we have to deal with the density. So here, in the rain case, we are dealing with the variability of drop size distribution. But in snow case, like due to the microphysical processes, like rhyming or aggregation, you will have a completely different density of snow. So that density should be taken into account when you get when you estimate the rainfall, snowfall rate from your measured radar activity. So here there is several thin line. It's all the literature relationship on the snow reflectivity factor and the snowfall intensity relationship. It's a little more equivalent. So you see a lot of variation from the case by case and relation by relation. And here we have 4 thick lines that relationship derived from the Marshall-Kalman drop size distribution with a different intercept parameter and 0 and with a different density diameter relationship. So here, like if you use the same intercept parameter about 0.05 and due to the change of density, like dry snow is a low density and wet snow is a high density. So in this case, you see for given rainfall intensity, you see the change of around the 3 dB change in your radar measurement. So that will again add up the uncertainty. So if you change it, let's say you keep the same density, let's say wet snow and wet snow here, but you change just the number density and the intercept parameter, and it's from 0.05 to the 0.005. Then you see almost 10 dB change, or a little bit more than 10 dB. So this from here to here is due to the change of the microphysics, and from here to change due to the density, number density, and from here to here due to change of the density of snow. So this indicates the density is extremely important to get the liquid water snowfall rate. So here again, the reflective high time cross-section of radar reflectivity and Doppler velocity. So you see the very shallow storm from the 1 to 5 UTC. And from looking at the reflectivity, you see the very broad feature, it's a very smooth texture around here, but you see a lot of small scale structure around here. So but the Doppler velocity provides much more information. Here you see the updraft around here. There is a pocket of updraft around this area. And also, if you look at the purple color, is a velocity larger than 2 meters per second. It's falling quick and fast. So in this part, in terms of microphysics or in terms of the density, they are falling fast, and this part is falling slowly. They indicate this is a low density and this is a high density. And also in terms of microphysics, this is more like an aggregation related to microphysics. This is a more rhyming process, dominant rhyming processes. So this is more like a qualitative interpretation. I will show you more quantitative verification. So during that period, they think about, you can actually at the same side we have snow size distribution measurement. from the optical zero. So that provides shape and also falling velocity for the individual snowflakes. From those equations, you can close the equation of motion by assuming some the friction term. So from there, since we measure the fall velocity, also we know the shape. Only a known parameter in that equation is density of snow or mass of snow. So from there, by solving the equation of motion, we can derive the actual density as a function of diameter for given period, this period and this period. So for the first period, the second period, you see the density is much lower. And the first period, you have a high density. So this prove again our reasoning. Warming processes and aggregation processes. So aggregation processes, we have a low density, and warming process, we have a high density. Okay, and also we should see I explained sort of conceptual model, how the dropside distribution change due to the different microphysical processes. So the warming process, you see the more like a parallel displacement of dropside distribution. And aggregation process, you see some sort of pivoting with respect to the medium mass diameter. So here, like here, for the warming process, you see the parallel displacement. And the aggregation process, you see the pivoting with respect to the medium mass diameter. So actual measured dropside distribution actually prove you see the parallel displacement of the source side distribution. And also in the aggregation process, you see the pivoting. So you have a lower number density for and also higher number density for the high rainfall intensity, and for the weak rainfall intensity, you have much steeper distribution. So you see the pivoting in your measurement as well. Now let's move to so far we are talking about precipitation estimate, how we can reduce uncertainty, or how you can quantify error in your estimate. So here, first step is precipitation forecast. You need to have a better precipitation estimate. Then, if you have an accurate estimate with an error structure, and also the radar can provide a lot of different information, like wind information, 3D wind, and also radar can provide the moisture. And also, pure polarization radar can provide microphysical information, whether it's hail or snow, or wet snow and dry snow. And also you can provide precipitation type too. And also from the clear air measurement, you can get whether there is a boundary in the clear air. So whether the air converges at the boundary layer. So using all this information, we can integrate into we can integrate all this information into a numerical model, and also we can use this information to do the radar nowcast. This is two way of doing the precipitation forecast. So I will show in the radar nowcasting, this is the observation and actual 4-hour forecast. What we are doing here, from the radar map, with the 2 radar map or 3 radar map at current and past information, then we calculate how the individual precipitation sector or cell move. And those are from the past information. And then using those past information, we extrapolate current radar map with those derived from echo motion. That's what we are doing here. So this is actual verification, and this is a nowcasting, 4-hour nowcasting. By just looking at that, you see almost two map are almost identical. So that proves the radar nowcasting provides really accurate information. On the other hand, from numerical model, you can integrate the radar measurement or all abundant information to generate precipitation forecast. So in the middle, this is verification from radar. This is a Canadian GEM model, and this is the WRF model. So the model is initialized at 00 UTC, and we consider the spin-up time up to 6 hours. So here I showed the only precipitation forecast from 06 to the 24 UTC. So here is just qualitatively what you look at here. In general, the WRF is too wet. Too much precipitation produced entire area. And GEM is too dry compared with the reality. And also, what you see is in the WRF model, the precipitation echo is almost stationary. It just keeps growing instead of moving. But that time, the advection is well captured in the Zen model, although it was too dry. So we see the lot of characteristics in there. Also, if you are talking in terms of intensity are completely different, completely wrong. And also in terms of location of precipitation forecast, the location is completely wrong too. So there is a lot of error in the intensity as well as the forecasting at the proper position. So that's a problem with the numerical model. So this is sort of a summary statistic from the numerical model and radar-based nowcasting. So this is the forecast skill. So if it is higher, then it means better forecast. So the radar-based nowcasting, again, for the initial few hours, its skill is extremely good because you are just using observation itself. But in the numerical mode, and then it drops quickly, since these types of forecast does not introduce any growth and decay in the precipitation. But in numerical mode, then it's almost flat. There is a little bit of a spin up down here. But it's almost flat. Eventually catch up the radar-based nowcasting. But this cross point is varies between the 3-hour to 8-hour forecast, depending on the weather condition, area, or scale that you are looking at. So this is sort of a summary which each one has a shortcoming and advantage. So for example, in the radar-based extrapolation, one of the strengths in this type of forecast is that it produces a precipitation forecast at a better location with a better intensity, and also structure of precipitation is much better. But this does not produce any initiation and growth and decay, because this simply we are extrapolating our measurement to the future. On the other hand, numerical model, the weakness of numerical model, it doesn't produce proper precipitation at proper location with the proper intensity. So this is the problem in the numerical model. But again, the numerical model produces some sort of information, initiation and growth and decay. So this is sort of the advantage in numerical model, regardless of whether this information is wrong or correct. So by looking at here, one's strength becomes the weakness, and one's weakness becomes the strength. So in this way, this provides sort of idea how we can prove precipitation forecast combining two products. So here, with the radar data information, the first step before combining two products, we have to improve individual product first. So from the precipitation, from numerical model side, we can introduce sort of sophisticated data simulation technique. That then will provide a better accurate numerical precipitation forecast. Maybe this will provide better information in the growth and decay. And also in the nowcasting side, we can improve the growth and decay information using the abundant actual observation. So individual ways for the numerical model side, we can test whether the effect of assimilating the radar data. So here in the middle is the model forecast. Actually, this is the current time. Forecast real time is 0. And actual current time, this is the initial analysis for the numerical model without radar data. This is model analysis period of precipitation at T0 with the radar data. And this is actual verification, actual radar measurement. So you see here, this is T0, and next to 1 hour forecast, and 2 hour, 3 hour, 4 hour, 5 hour, 6 hour, 5 hour. Over here, in general, let's see the 3 hour forecast. Even 3 hours, without radar data, you don't see the actual precipitation pattern. There is a lambda-shaped pattern around here, but that information does not produced by the numerical model without the radar data. But that information, that shape, precipitation feature were captured with the radar data simulation. So this is even for the 5-hour forecast, still our forecast with the radar data is much better than without radar data. So this is a way of improving the precipitation accuracy of precipitation forecast in numerical model. And here this is Q score. So this is the critical success index and correlation as function of forecast time. So here without radar data, with the radar data, there is significant improvement in the skill score. So in this way, we can improve our forecast. Originally, the numerical model was so flat and very low skill score, but with the data simulation, we can improve our skill dramatically. And another thing is, now to the other side, how we can improve extrapolation. So, because extrapolation has a problem with predicting initiation, growth, and decay. So that can be introduced from the observation. So we want to combine the extrapolation with some growth and decay information. So that can be introduced by the actual observation. This is sort of the variational data simulation analysis from VIDRAS, developed by ANCA by Jenny Sun. So this is, you see the wind information vector around here, and they see the convergence around here. So we have a convergence line along this line, but the activity is still very weak around here. So only when you see the strong cell along this direction. But you see the very strong, the convergence around here. And this is purely from the radar, but we can do the similar analysis from satellite and actual surface observation too. So in that way, we can calculate whether this area will be, the storm will be developed along this line. And then we can predict 1 hour later, this area will be to grow. And then actually we can verify with the actual measurement. This is the one way of introducing growth and decay in the extrapolation. In this way, the skills we can improve skills for at the initial 1 or 2 hours. So this is a combination of extrapolation and initiation growth decay from the actual observation. So now we have extrapolation with the growth and decay information and data simulated numerical model forecast. So now we can combine those information. So in this way, we can minimize the shortcoming problem for each component and maximize some advantage of two components, two products. But there is a lot of issue actually. So numerical model has a problem with predicting precipitation and proper location and with the proper intensity. But the radar extrapolation provides better information in terms of location and feature, but doesn't provide any intensity and growth. So here, this is 6-hour forecast, and 6-hour forecast from radar and the numerical model. You see how they are different. So they are completely different locations. So one of the issues is how you can combine these two. If you just do the simple two averaging, then you will come up with the whole area will be predicted precipitation, all the area. So that's a problem. So first step is, somehow you have to correct maybe positional error in numerical model. So that's the first step. So you have to shift all the precipitation forecast from numerical model into the proper position. That's the first step. Or correcting the uncertainty in the precipitation forecast numerical model with the actual observation. So this is compare numerical model forecast, precipitation forecast from numerical model and actual verification. By comparing two, we know this area model completely missed precipitation. So we call the miss. And also there is a false alarm, so there is no much precipitation around this area, but the model actually predicts precipitation around here, and even here too. Very weaker and very small cell around here, but it's a strong cell around here too. So we call it as a false alarm. And also, if you look at this area, actual precipitation area is here, but if you compare with this one and this one, this is actually model predicted precipitation around this area rather than here. So you see there's some uncertainty in the location too in your precipitation forecast. So we call that as a phase error. Phase error can be done in terms of space as well as time too. And also here, this area. And also if you look at the entire precipitation feature, model is more like south and north elongated. But here you see the more curved shape in your precipitation feature. So that's due to all the uncertainty or error in the phase, locational error. So also of course there is an intensity issue there too. So what we are trying to do is we try to correct numerical model forecast to have a perfect radar map. So what we are doing is we are deriving phase and intensity error. So when you say the phase error means the locational error, intensity error means it includes all the false alarm and misses everything. So we try to quantify the model error in space first, So that's what we are doing here. So basically what we are doing is we try to get the sort of model phase error, model intensity error, which we call the morphing factor, to convert the model map into the radar map. That will be our spatial model error in terms of phase, location, as well as intensity. So that's what we call the power. So this is space-dependent error at T0. And that way we can convert the model field into the completely radar maps. You see how the location can be improved, corrected. So original location of precipitation focus was maximum around here, but they are slowly shifted to the proper position here. So that's what included in the morphing factor, phase error, the model error factor. And then we derive this morphing factor at T0 and repeat this time procedure for the past information. So we are calculating model error at T0 as well as we are calculating from the past error, past information too. So in this way, let's say we have full phase error from current to the 3 hours before. So this is the same model forecast. From here, what you can do is you can calculate the tendency over each model error in space, in positional error, as well as intensity error. And then what you can do is we are at time, right now we are at the current time. We know that in each position we know the tendency of a numerical model forecast error. And then what you can do is we can calculate actually how much model error we expect after 3 hours. So in this way, we can correct 3-hour forecast with this tendency derived from the current and past information. So this is sort of a general concept. So there is a lot of mathematics within there. So in this way, this is the original forecast, but with this tendency information of numerical model forecast, then we can correct actual numerical model. But this concept is based on the model has consistency. So let's say model forecast, precipitation forecast at this place at the T0, and suddenly go to a completely different place and here, jumping around here, that means the model doesn't have any consistency as a function of time. But that's a really bad model. You shouldn't believe that types of model. But at least, maybe you may have some intensity and phase error, but still, let's say at T0 you have this amount of the locational error, but it may be slowly reduced or slowly increases. So at least you see some tendency as a function of time. So all this correction algorithm based on those consistency of numerical model error, which should be in the numerical model. Otherwise, nobody will believe numerical model. So we apply this kind of new correction algorithm into the many data sets, like the numeric GEM model and MemFile and WORF model. I will illustrate just the result. So here, this is the 3-hour actual verification from radar, and this is the original 3-hour forecast from numerical model. And here what you see in this area, you see the positional error in the numerical model, as well as intensity error. So pattern is completely different at completely wrong place. So with the phase correction only, locational error correction only, we are talking 3-hour forecast from now. It's not a current information. So here, we now, applying phase correction, we now put the precipitation pattern at the proper location. But phase correction doesn't do much in terms of intensity. But with the additional amplitude or intensity correction, now we produce proper precipitation intensity. Now the shape is better compared with the original forecast. And also this place, the model completely missed precipitation around this Florida area. Phase correction doesn't do anything. But with additional amplitude correction, we generate new precipitation around this area. So again here, here, phase correction doesn't do much around this area. There is a difference in the intensity, but with the intense correction, we have better produced precipitation. And here, the shade is better predicted compared with this one and this one and this one. So with intense correction, you see the better shape now. So this is for the 6-hour forecast after correcting. So still you see the improvement in here. Here you have a new precipitation. So actually the model start to keep, the previous precipitation. There is some delay in time actually. But the actual correction intensified precipitation on this area, which is more close to the actual reality. So still we see the improvement for the 6-hour correction, 6-hour forecast. So this is summary statistics. We did this summary, this year we showed about 10 days of forecast. But I did this types of verification for the almost more than a month of data set for the different numerical model. And this is just one example. Here, this is the original forecast. Here, model skill score at CSI is completely very low, 0.2. This is a very small measure scale, about 1,000 by 1,000 kilometer domain, with a 5 kilometer run model resolution. So this is Indiana and Illinois area. So during the summer period. So you see this time of period, you see the lot of convection in this area, and in this case, the scale in the American is very low, it's 0.2. So I don't know whether we really should believe numerical model with this kind of low skill score. But with the phase correction, you improve the overall for the entire period. With the additional intense correction now, you significantly improve all the skill score throughout the period up to 13-hour forecast. And definitely we can compare with the extrapolation technique. So for the initial few hours, definitely 1 or 2 hours, the extrapolation is better or they are compatible. But the later time, 3 or 4 hour forecast or our numerical model is better. But originally it was more or less similar or slightly better, but now we improved significantly throughout the period. So far what we did is, using radar data or observation, we tried to correct the numerical model data. So next step, right now, what we are doing is we are doing the actual feedback of this process into the data simulation. So we can introduce these phase and intensity information and correct your background field. So right now, you are doing the data simulation with a model background, which is produced from the previous forecast, and mixing with observation. But those model forecasts, it has a lot of uncertainty in terms of locational error and intensity error. So we correct those information and introduce those information into the data simulation. Next step is we are exploring sort of a new field. So we know the radar exploration always better for the initial couple of hours, up to 3 or 4 hours. What we are trying to do is we actually doing the data simulation for the current and past information. We try to assimilate a future actually. So far, when you do the forecast, then you don't have any actual observation in the future from T0. But from the nowcast, we have an actual forecast, which is better than the numerical model forecast. What we are doing is we are doing sort of a simulation of future observation. We are generating future observation with the radar nowcasting and assimilating those information into the future. So that's a sort of a new way of looking at the field. And another thing is, after phase correction, we are doing the sort of model error correction in a deterministic way. But they might have a lot of uncertainty in our corrections. So there is some residual uncertainty in your model error. So we try to generate ensemble with those model error and introduce into the data simulation. Another thing is we know that there is an error structure in the radar precipitation estimate, and then that should be integrated into the ensemble generation and then introduced into the numerical model, rather than just directly assimilating radar deterministic QPE into the data simulation. And the other step is in the gross and we introduce gross and decay information, but in those corrections we have a lot of uncertainty. So those uncertainty can be introduced into the ensemble generation and then also integrated into the nowcasting too. So this is sort of a new future work, and some field already we are doing some work already. So I will show an example how we can generate ensemble. Here we are talking about ensemble generator to generate ensemble data simulation or ensemble nowcasting. So in there one of the key issues is how you want to generate ensemble. So whether you want to generate ensemble completely random, but that's not true. We know there are a lot of structured error in your QPE. And even you will see a lot of structured error in this correction as well as growth and decay, uncertainty in the growth and decay as well. So we need to find a way of generating ensemble with a spatial and proper spatial and temporal structure of error. So here, this is I will introduce one example. For example here, this is a radar measure reflectivity. In radar QP, what we are doing is we are estimating radar rainfall intensity with known GR relations. But we know this has a lot of uncertainty in this estimate. So actual true field should be a combination of this deterministic field plus uncertainty field. So, but this uncertainty delta should have a structure in space as well as in time. So that's a proper way of generating ensemble. So here, previously I introduced, if you, in the GR transformation, there's a lot of uncertainty. Those uncertainty has a time structure. Those uncertainty last longer than 1 hour. So we know now, from actual observation, we know the structure of your uncertainty. So what we are doing is, from these actual measured uncertainty, you can generate many different member of ensemble with maybe with just a typical Fourier transform, right, or self-alpine realization. Or you can, if you know that if you have a lot of different information in different locations, then you can build up the full error covariance matrix. From there, you can build the different member of ensemble by adding the uncertainty that has a proper spatial and temporal structure. And then we can add this different uncertainty, the realization of different uncertainty into the deterministic field, and then generate the ensemble QPE. Then we can introduce this into the data simulation. So this is an example how they look the actual deterministic R field from radar. And this is deterministic R field plus introducing uncertainty in QPE. But data R has a structure in time as well as space. So here, by looking at these two, you see that in general feature, they're very similar for the overall area. But if you see the real detail, look at here, down here, even here, you see the quite different structure here. There is stronger reflectivity, weaker, much weaker. And here, you are losing some feature out here. Also around here too. You see if you see the real detail there, you see a lot of difference in your actual member ensemble. So this is an example how for the full realization of ensemble, this is the deterministic field. And this is member 1 and 2, 3, and 4 with introducing same error structure in time and space. But if you see you compare the realization with the actual deterministic, they are completely different in some cases, like for various people. So here, if you look at this area, compare this 4 member, they are completely different, although they have the same error structure. So this is one way of generating the proper member of ensemble, rather than generating ensemble member in a completely random way. This is more based on your actual observation, uncertainty from your actual observation. So this is, I'm just talking about the uncertainty in terms of QPE. But we can quantify the numerical model error in terms of like a diurnal cycle. So model has systematic bias in the producing diurnal cycle. And also maybe there is a lot of systematic uncertainty in the orographic precipitation pattern too. Also, we can introduce favorable condition or model tendency we introduced like in the new correction technique. So this all information can be introduced into the more ensemble generation, and we can do the sort of ensemble nowcast. I think I will stop it here.
Okay, thank you. Your question.
Well, it's a very interesting talk. I really enjoyed. I think the concept is quite challenging. But essentially you are doing is try to utilize the numerical model, whether it's research-oriented or operational-oriented, use this prediction, expression prediction, and try to match that with observation, primarily from radar observation. And we all know that any given model, whether it's operational or research model, has certain limitation and uncertainties. To our understanding, most models usually could not predict the subscale processes. That's due to many reasons, and one of the widely cited reasons, of course, is the so-called precipitation, parameterization scheme used. That's, of course, primarily to the resolution. There's a definite limitation to reduce the resolution of the problem. And we have to deal with that because that's what probably the ultimate limitation that we all have to face. So the next step is to how do we deal with that? How do we go from there using the most available model physics and its resolution that we can deal with and try to improve the product model compared to observation, specifically radar. My experience in the past is that we have also done several simulation studies. We found that in some cases the model can do very well, such as case involving well-organized, strong forcing collective activities, such as the score line, where some well-organized scales. That model can do well because the propagating speed of that seems to be somewhat controlled by the model pretty well. The case you showed there, if you assume that the model is going to predict the effective speed, which probably not in agreement with the actual observation, could this be caused by the other factor? Let me give you another example. Some studies also suggest that for more isolated convection, like instead of organized convection, isolated thunderstorm, many of these thunderstorms can produce co-op flow. And the co-op flow, as we all know, can initiate new convection. And if the model fails to predict that thunderstorm activities, and then subsequently it will fail to predict the initiation of the new convection.
Right, exactly.
Therefore, a lot of this disagreement could be not because of the advection speed itself. It could be some activity the model is simply not capable of predicting.
Right.
So this seems to be a widely spread problem, especially in Florida, for example, in this area, where less organized convection seems to be very common. So can you comment on that? How do you resolve that? We simply cannot assume the model is perfect.
No.
But we have to use it.
Yeah, we have to use it.
Right.
The first one to use model is you need to understand the numerical model first.
Yeah.
So like you mentioned, there is some cases model predict better, right? And some cases you don't know the model really works to predict proper precipitation. So if what basically we are assuming is model has some sort of minimum skill. At least it does something. If it doesn't do anything, then this kind of technique cannot do anything. It's basically we are thinking model has a sort of a decent skill, some skill, but it's not perfect. So that's why in that case, we usually do it, to do this kind of thing, we do a lot of verification of numerical model. So whether we see that you are consistent in your numerical model. But if you don't see any consistency, then we shouldn't apply any correction, because model is completely wrong, then we cannot do much. So, but what we think is, as parameterization increases, maybe resolution increases, model still score become better and better and better. So if that can be achieved, then a lot of hope we can do better job. Simply rely on numerical model itself, but you get a lot of new field you can do the improve forecast in terms of post processing.
Okay, the second question. How many cases do you think you need to establish that statistical relationship? Because in order to be viable statistically, sample size definitely is important.
So in this case, actually what we are doing is, it's the derivation of the tendency of numerical model data is more like adaptive. So if you have one forecast, then you can calculate all the tendency for those given forecasts, rather than going back to all the statistics. So in this sense, we don't need really lots of statistics for this case. Only the way we can verify whether the model is really performed reasonably well is after correcting all these things, let's say we can apply this correction for the months of data. And then definitely you will see that some cases the correction doesn't perform well, or it's exactly the same as the original forecast. But in statistical sense, we see that in general there is significant improvement for most of the cases. At least the 70 more than 70% of cases. That already proves model has some skill, and there is some hope in there.
And the third question is, how do you think that since a lot of these precipitation activities could also be affected by terrain and the climate as well? Supposing if you decompose that, the United States, certain regions, and combining your statistics, probably doesn't mind come up different statistics.
Exactly.
Instead of looking at the entire map, because you involve different type of correction.
Actually, this correction is grid by grid. It's not just one statistical entire field. So in each about 50 by 50 kilometer resolution, we have one correction factor. So it's all space dependent as well as time dependent. So but already within the whole statistics already built in within the algorithm.
Very impressive.
I have two questions. First one is I'm not quite sure about your best correction. For the procedures, did you correct the best on the grid scale or you track the system?
It's to calculate the tendency of the model, you need to track backward for the individual grid or individual cell. So in that way, let's say you have one echo here from model, and we have one echo from the radar map. We know that this echo is the same thing. But at T0, we have a sort of phase error. But what you can do is you can track back how this history of this the individual cell. In that way, you know whether the phase error or locational error increases or in terms of in the X and Y.
So you need a manpower to go
No, it's everything is automatic. Yeah.
Okay. Now my second question is your method seems very depends on the distribution of your radar network. So for such kind of system, what do you expect your minimize or your optimize distribution of your network, your observation network?
So first step is we need to have a good quality of precipitation QPE product. So that's why I introduced all different stuff. How you can reduce this error and uncertainty to DSD variability, and also there is uncertainty to the radar calibration and continuation, everything. That should be corrected first. So in that way, first step is we want to have a real as accurate as possible in terms of precipitation map. And also, we need to have a lot, the high resolution information too. So that's the first step. To get that, I don't know, it's all the network of radar, depending on the location. Let's say, like a mountain area in Taiwan, definitely the operational radar, typical like 100 kilometer space, doesn't give much information. You lose all the information along the mountain area. So in that case, you may need to consider maybe small X-band geopolarization radar in the valley sometime. So in the one it's a hybrid types of the radar network. Like you can have a big coverage in the radar with large radar like S-band radar, but the large radar cannot see the S-band radar cannot see the small area in the valley area. Then you need to cover that area with a very small span radar. So I think there is a more real solution or answer on that how we can optimize network. So that's all depending on where you are dealing with, what kind of a scale you are dealing with. Let's say if you want to have just let's say 100 by 100 kilometer QPA product, then that's a different issue too. But if you want to have a QPA product 1 by 1 kilometer, then you need to have a much better layer network.
So in this case, I have another question is, for this very large area in the United States here, you have a very intense network along the coast, but in the middle they don't have much. And what if you have a long existing system which move from the coast domain here into the inland domain now, and can your system have some objective scheme to choose your best? I mean, your statistical, like a lookup table or something like that.
But actually, you don't have observation, you cannot do anything. So there is always a limitation with the observation. But one thing we are exploring is applying the satellite data. So instead of dealing with all this question in terms of in precipitation estimate, maybe you can deal with it in terms of water vapor. So particularly like you have a water vapor channel, and then you can from the numerical model you can calculate the water vapor channel with what's called observation operator in the data simulation, etc. So in there you have observation from the satellite, you have a numerical model calculated pseudo observation, then you can compare it to. So they will cover the entire domain.
Anthony, when you talk about correct the phase and the intensity errors, I'm wondering, are you using any wind information? Wind velocity? It seems
This
yeah.
No.
You only use reflectivity.
Yeah. So we are not going back, we are not touching any dynamic field at this stage. Since our final product is precipitation, so we want to touch with the final product. But the next step is what I'm talking about, when you correct the phase error, then we can apply those corrections to any dynamic field, hopefully. And also any different thermodynamic field, if you have observation. Then you can go back to the numerical model. And then you can generate the numerical forecast again. So but right now we are not doing any correction in the thermodynamic field.
Also in the maple system.
It's only precipitation.
In the maple, you also need a 3D wind to understand.
No. It's a tracking, motion tracking of individual atom.
Track. But you need to make forecasts.
But we are assuming the past motion of an echo is still persistent in the future. Now one way you can do is you can maybe use steering level wind for the vector system to make a forecast.
Any more questions?
Yes, I have one question. It was about this phase and amplitude error. Because you have different lifetime scale within the whole system. So when you track back, some probably already disappeared, but some still exist. So you go to the longest, I think, the oldest system, the oldest and most persistent system for your track back. So how long you say you track back? A few hours?
Usually we track back, depending on the scale you are dealing with. When you deal with the content scale, we usually use past 3 or 4 hours. But if you are dealing with a very small domain, like with a scale domain, we use a very high resolution model output for the past 1 hour. But like the question you asked whether system disappeared or you have new generation, that's a very tricky part because you don't have information in there.
That's right.
So what we are doing is in the algorithm itself, we build up the smoothness constraint. So like you have a big cell here, another cell here, and then this cell you have new generation here. But you don't see this information in the past. But for the phase error at this place should be somehow continuous in space too. So that's how we build up the calculating phase error.
So you smooth your
Yeah.
to get
Yeah.
pattern first.
Right.
Okay.
Another question is, you mentioned, because that slide go very fast, you mentioned you can use the real true reflectivity and the forecast the error as a background error, right? You mentioned in the
No.
slide.
What we are doing is trying to compare observation with a numerical model background, and then correct your background, and use those corrected background into the numerical model for the data simulation. But it's like explicitly correcting model errors instead of to correct the phase error or model error, you need to know the full error covariance matrix, which is the impractical. So without knowing the full error covariance matrix, just assuming the diagonal component, then there is no way you can really correct those large phase error. So what we are thinking is those large systematic error should be corrected first, and then we have to do data simulation.
Okay, any more questions? Dr. Lee, in the beginning of your speech, you mentioned that fuzzy logic is applied to the reflectivity and radial velocity in the conventional radars. And you got a better result in rate estimate. And the pattern of the map seems very similar to the dual-pole radars. And did you compare the accuracy between the two methods?
Actually, we use the qualitative approach as truth, and then calculate the skill score in your algorithm. So that provides around 0.8 for the CSI. It's pretty high.
How did you determine the weighting functions?
So, okay.
Empirical or theoretical?
It's, I would say more empirical based on the data. So basically what we are assuming is, one of the big problem in these kind of ground curve AP elimination is where you have a mixture of AP and precipitation. So within 1 second volume, you have 2 types. So those types, there is no way really you can identify. So what we are trying to do is, we go back to the old clean day. So like there is no precipitation, it's clear day. There is no precipitation. We know all the data echo is coming from the ground level or anomalous propagation. That's our data set for the precipitation in the ground level. So from there you can calculate all the features. So that's one data set. There is another data set. Is now when there is no anomalous propagation AP, then only the ground cloud, the normal ground cloud area is actually affected by ground cloud. So you can just choose precipitation area. So from there you can calculate the feature. That's another data set. Now we have 2 data sets. From 2 data sets you can calculate the frequency distribution. So we can, within one frequency, let's say, radial velocity domain, radial velocity versus actual frequency distribution versus radial velocity. Then you can have a 2 frequency distribution from ground level and from precipitation. So downward you have two distribution. So if you have a lot of overlapping between two distributions, it means that parameter is not a good parameter. You have to give a smaller value. If you have the two distributions completely separated, then you have to put the high weight. So you can do the sort of math in there. You can use area as a weighting with the sort of inverse of the area. So that is, if you are interested, I can give you the paper.
Thank you. Okay, any more questions? Okay, if no more questions, let's thank Dr. Lee again.